Alright guys, welcome back to your online geometry instruction. Today we're skipping ahead to chapter 12, talking about tangent lines. Chapter 12 is all about circles, so we're going to be discussing a lot of characteristics of circles that you probably have not seen before. Now, when I say tangent here, I'm not referring to trig. Okay, I'm not referring to trig, so I'm not dealing with the tangent function anymore. Okay, so I'm not dealing with trig. This is a different definition or a different concept, same term but a different concept than taking like tangent of an angle or sine and cosine. So this is not trigonometry, it's different. Okay, it's different than that. Let's look at what it means first, and then we'll do a couple of examples together. We'll finish with the most difficult example, I think, in this chapter. It usually gives students kind of a tough time, so we'll finish with that. So let's first do some vocabulary. Alright, so a tangent line is defined as a line that touches the circle only once. Only once. So you can imagine, if you want to picture like a real world circumstance, like if I have like a soccer ball, for example, and this is going to be a terrible sketch of a soccer ball, but if I have a soccer ball and I need to, if something's like resting on it, like here's my soccer ball, and let's say I have like a book or some sort of my coaching clipboard or something like that is resting on it. Well, it touches exactly once at this spot right here, right? So we could say this clipboard here is tangent to the soccer ball here, meaning it's only touching once, okay? Looking at this picture here, because we're not going to talk about soccer balls and clipboards, I wish, but we're not. We're talking about a line here, AB, that is tangent to circle O, because AB only touches circle O one time. Okay? It just rests on top of it. It doesn't slice through it, and it doesn't miss it entirely. It just rests right on top of it. Okay? Now, that point that it touches, this point here, point P, that point is called the point of tangency. So it's the point, to define it, it's the point where a circle and a tangent intersect. So to tie that into this to this picture here, we have a circle O, and we can say that AB, line AB, right? This is a symbol for line AB is tangent to circle O, which the notation for that is as follows, to circle O. And then we would say that P is the point of tangency. So point P is the point of tangency. Okay, so that's just a little vocabulary for you. Now there's a theorem for you. It says this: if a line is tangent, again meaning only touches once, it's tangent to a circle, then it is perpendicular to the radius. It's perpendicular to the radius at the point of tangency. So we know, or it says, if a line is tangent to a circle. So here's my hypothesis, right? If a line is tangent to a circle, which we say that AB is tangent to circle O, then it is perpendicular. So we know that it is then going to be perpendicular here to the radius at the point of tangency, so at point P. We can say that OP and AB are perpendicular. So OP is perpendicular to AB, or we call it line AB if you'd like. Okay, so that's what the theorem says. if it's a tangent line at the circle, then that place where they meet, that would be a perpendicular intersection. Okay? So, if I know that these two lines here are tangent to the circle, okay? I know they're tangent to the circle. Then I want to find a value for x, given that this angle here is 140 degrees, okay? Well, again, we have a radius, right? Here's the center of my circle. We can call it C. We have a radius here, and we have a radius here. They're going to have similar characteristics because, again, these points down here are the points of tangency, which means at each of those points we have a perpendicular intersection, right? So really, we have a quadrilateral. In fact, hopefully you'll notice later that it's a kite, okay? We have a kite that's formed here with this shape, right? And we know that these two are both 90, here and here. We know those are 90. So the other, well, all four of them add up to what? It's a quadrilateral, which means the four angles, the interior angles, sum is, so add up to 360 degrees. Well, we know we have 90 and 90, so really the other two must add up to 180. Since we have 90 and 90, well, that takes away 180 of it, right? So that's where this comes from. So we can just say that x equals 40 degrees. So you can even skip this step here and just say, well, these two angles here must be supplementary at all times because the other two are always going to be 90 degrees. Okay? So we can say that these ones here are supplementary, leaving us with x equals 40 degrees. Again, supplementary means they add up to 180. Okay, so that's kind of how that works. You can use the fact that they add up, or that they're perpendicular at these points here, at the point of tangency, they meet at 90 degrees, to find the angles, or the angle measures, inside that quadrilateral. Okay, so that's just kind of, little mechanics of it. So, another theorem. If a line is perpendicular to a radius at its endpoint on the circle, then the line is tangent. So we're trying to figure out, is AB tangent to circle C? Okay, so is AB tangent to circle C? So let's use this theorem to our advantage. If a line is perpendicular to a radius at its endpoint on the circle, then it's tangent. So we need to see, is this 90 degrees? If it is, then it works. Well, what's the information we're given? We're given that AC is 3, so the radius is 3. We're given that AB is 4, and we're given that BC, this whole segment here, is 5. Well, you can use the converse to the Pythagorean theorem. Say if 3 squared plus 4 squared. We're trying to see if that's the same thing as the hypotenuse, then it's a right triangle, right? Which is what we want. We want this to be a right angle. We want this to be a right triangle. 3 squared is 9. 4 squared is 16. And we want to see, does this equal 25? Well, what's 9 plus 16? It's just 25. So since they are equal, then we say, yes, it is a right triangle. Therefore, it meets at 90 degrees. Therefore, as the theorem says, it is tangent. So the answer here would be yes, it is tangent. Okay, so again, the mechanics are, if we can see that this is 90 degrees, if we can prove, using the converse of the Pythagorean theorem, that it is a right triangle formed here, then it must be a 90-degree angle, therefore it must be tangent. Okay, so again, these are kind of new mechanics. It's just kind of the basics of circles, so you'll get the hang of this. This will become second nature really soon. Okay, so don't get discouraged if you got a little lost there. You had to rewind and repeat. That's okay. Now, another theorem. I believe this is the last one, so don't get too devastated. Okay, so the two segments tangent to a circle from a point outside the circle are congruent. So let me piece this together for you because it's worded a little funny. So it's saying we have a circle here. We can call this circle C. So this is its center right here. Okay. We have a circle, and we have a point outside of that circle, we'll call that point P. Now from that point, I can draw a tangent line here, or I can also draw a tangent line here, right? I can draw a tangent line to either side, and it doesn't matter which one, right? You can always draw two tangent lines to a circle when you have a point outside the circle. What it's saying is that this segment, so just the part of the segment that right here to the point of tangency and right here to the point of tangency, again, these two segments in black here must be congruent. Okay, so the two segments tangent to a circle, so these points, let's call this, if we call this A and B, we know that PB is tangent, and we also know that AP is tangent. They share the common point outside the circle, i.e. point P, right? They share that, which means that we can say that PB is congruent to, I'm going to say PA, just to keep the points in the same order. Okay, so this is what the theorem says, that they're the same length. Now this leads to a pretty cool example. This is my favorite type of problem in this chapter, so pay attention to it, because I like to ask it, and you can do different things with it. Okay, so this problem here, it says that circle C is inscribed in triangle XYZ. Okay, and again, inscribed just means, inscribed here, this term, means that it is only touching each part of the triangle once, which means that, pardon me, each of these segments here is tangent to the circle. So that's all that means, that when it says inscribed, it means each segment is tangent to the circle. And we're trying to find the perimeter of that triangle. So let's, again, what does this theorem say? Each, from the point outside the circle to the point of tangency, those segments are congruent, right? So if we're here, we're looking for specific congruent segments. Well, okay, we have a point outside the circle here at X, which means this segment and this segment, both of which go to a point of tangency, right? We have those two segments must be congruent, therefore this top segment must also be 4, right? Same concept here. We have, let's look at point Y. No, let's not look at Y yet. Let's look at it after. And I'll show you why. Y and Y. That's funny. Alright, so we have point Z here, right? We know that this is 6. The other tangent segment here must also be 6 because they're congruent, right? And the reason I want to know that is because now I can say that this segment here is 3 because 6 plus 3 makes 9, right? So I can piece, that's why I had to do Z first, because I needed to know this segment length here in order to then find this one here. Okay, so I know then that this little one is 3 right here, which means this one next to it is also congruent, which means it is also 3. So really I have 9. That's, let me do a different color here. Let's go with purple for fun. I have 9. That's the length of this whole segment here, right? So that's 9. The length of this whole segment here is just 4 plus 3, which is 7. And the length of this segment here is just 4 plus 6, which is 10, which gives me a perimeter of 26 meters. So again, the points or the segments that come from a common point, so 4 is congruent to 4, 6 is congruent to 6, and 3 is congruent to 3. Okay? So that's kind of how that problem works. That one's a little trickier. You need to really make sure you pay attention to the details there. Other than that, though, we have one more problem that I will save for the next part, and that is the wonderful bicycle chain problem. It's kind of a tough one, so we'll save that for part 2. So be sure to watch it. See you.